shop down in Old Soho, where you drink champagne and it tastes just like cherry cola. C-O-L-A cola. She walked up to me and she asked me to dance.
Okay, in section 4.4 we're going to learn how to solve exponential and logarithmic equations. Just like other equations that you solve, your goal is going to be to isolate the variable, get the letter by itself. But now you have exponents and logarithms to worry about. So I have a few rules for you here that can be helpful. One is that a to the x power equals a to the y power if and only if x equals y. So this if and only if, this is a mathematical expression. It's used in logic. You can actually write that as if. Yeah, with two f's. In math you can spell if that way. It's different than this. This is not the same thing. If just means if. If means if and only if. And what if and only if means is this side is true if this is true, but vice versa. This is true, x equals y, if this is true. So this works both ways. So this will help you out, because if you know that, for example, if you get down to a step like 5, we've talked about this already, 5 cubed equals 5m, then you know, since you have the same bases, you know that the exponents have to be the same. It also works if you have that 2 equals n, you can raise those to anything you want. Okay, I'm going to raise, sorry, you can raise any base you want to these exponents. 7 squared equals 7 to the nth power. Those must also be equal. Alright, here's another if statement. If base a logarithm of x equals the base a logarithm of y, then you know x equals y, and it works backwards as well. If you have two numbers and you take the same base logarithm of each one of them, it'll be the same. And the last thing is, this is one of these cases where we're solving equations, you need to look for extraneous roots. Why is that? Because remember in the base b logarithm of x, x has to be greater than 0, b has to be greater than 0, and b cannot equal 1. So when you're doing these, solving these equations, sometimes you're going to get answers that are less than 0 for x, and then you'll have to get rid of that, reject that root. Alright, let's try a few of these. So the first one here, 3 to the x power equals 19. The way we did this before was you tried to get the same base, but we can't get the same base. I mean, 19 is a prime number. There's nothing we can do. So your strategy here, for almost all of these, I'm going to only say this once, but just keep remembering this. There's multiple ways you can solve a lot of these. So if I'm solving this in some way and you're like, wow, why is he doing all those steps? I could have done that in half the steps. Great. I'm sure there's going to be a couple steps or a couple questions in here where I don't pick the optimal way of doing it. If you got a better way to do it, great, as long as it works. You got to use those rules, those laws that we talked about last time, basically, to solve these questions. Okay, in this case here, what you could do is you could take the logarithm of both sides. Which logarithm might be wise to take? You could take any base you want. Why don't we make it a common logarithm of 10? You don't have to, but it's probably the best, because then you can use your calculator. So logarithm of this side, 3 to the x power, equals the logarithm of the other side. Now you see this exponent here of x, we have the power law, and so remember we can scuttle that x out to the front. I'm now totally committed to using scuttling for the rest of my teaching career. Scuttle that out to the front, and you're left with this. Our goal is to isolate the x. Well, that means if right now we have x times log 3, that's what this means, guess what we're going to do to get the x by itself? We're going to divide by log 3. So you get log 19 divided by log 3. And then you're either done if they just ask you to solve it in terms of logs, or you could go to your calculator. I'm not going to grab my calculator here. I'm just going to write down the answers. When I get the common logarithm of 19 on my calculator, I get 1.27875, blah, 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 goes on and on. And when I get log 3, I get 0.47712. And when I divide those two things, I get 2.68. By the way, does that answer seem about right? Well, let's think about this. We're saying that 3 to the 2.68 power equals 19. What's 3 to the 1 power? 3. What's 3 to the second power? Whoops, 3 to the second power? 9. What's 3 to the third power? 27. If we're looking for 19, that falls somewhere between 9 and 27, so it must be 2 point something, and it seems that, well, it doesn't seem, 19 is a little bit closer to 27 than 9, so if I was estimating this, I'd probably say around 2.6. And it turns out it's 2.7, so I'd be a tiny bit off, but it's a pretty good estimate nonetheless. And yeah, I feel really confident about this answer. So you can think about it that way if you want, to see if you're on the right track or not. Okay, next one. We want to figure out what x is here. Let's isolate the logarithm. This is often going to be a great strategy. So we have the base 5 logarithm of 2x equals negative 1. Move the 1 over and it becomes negative. Okay, now what we could do is we could turn this logarithm into exponential form. So the base is 5, the exponent is negative 1, and the argument is 2x. Hey, this is looking more like something we could solve. 5 to the negative 1, well, we can simplify that. That's a flippin' negative, so 1 over 5 equals 2x. Got to get the x by itself, so what are you going to do? Since this is 2 multiplied by x, you're going to divide by 2. So you get 1/5 divided by 2. That's the same as 1/5 times 1/2. You'll get 1/10. Yeah. Again, we could isolate the logarithm. Well, actually, it already is isolated here. So we could immediately change this to exponential form. What's the base here? It's the common logarithm, so it's base 10 squared is the exponent equals 3x plus 7. Oh, this one's not too bad. So 10 squared is 100 equals 3x plus 7. Take away 7 from both sides, you get 93 equals 3x. Divide by 3. I'll show it here. I don't know why. You get x equals 31. Of course, as always, if you're not sure of your answer, and this is a great way to check for extraneous roots, you can plug it in to the original question and see if it works. So let's try it. 3 times 31 is 93, plus 7 is 100. So we end up with the common logarithm of 100 equals 2. Is that true? Yeah, because that's base 10 squared is 100. Yep, that works, so we know this is correct. Alright, now we've got a whole bunch of logarithms here. Let's see if we can combine some of these logarithms. We definitely can on this left-hand side. We have 2 common logarithms, they're the same base, and we're adding. So to remember what that means we can do? We can actually take both of the arguments and multiply them. So we're going to have x times x minus 2 equals log 15. Now, we have logarithms on both sides of this. You can't, okay, so if we have logarithms on both sides, that means that the argument here, x times x minus 2, has to be equal to the argument here, 15. You couldn't do that here. You couldn't say at this step that x plus x minus 2 equals 15, because you have 2 logarithms here. You have to have one logarithm on this side, one logarithm on that side, so watch out for that. It's a common mistake. Okay, now we're back to a quadratic equation from last year. We can solve this. Mountains, we get x squared minus 2x. When you have quadratic, we like it to equal 0, so let's move the 15 over. You get minus 15 equals 0. Factor that, x minus 5, x plus 3 equals 0. So you end up with an x of 5 here and negative 3 here. Don't forget to check for extraneous roots. There's one of these that won't work. Which one? The negative 3, you can't have a value here that is negative, so only the positive one works. And so x equals 5 is your answer. This is a reject. Okay, next page. They are getting harder and harder, and I'm sorry about this. They're not easy, I know. Okay, on the left-hand side here, we can again combine our arguments. We're using the quotient law this time. So base 2 log of x plus 3 divided by 9 equals 4. And we don't have logs on both sides, but we could now turn this into exponential form. 2 to the 4th power equals x plus 3 over 9. 2 to the 4th power is 2 times 2 times 2 times 2. It's 16 equals x plus 3 over 9. Let's multiply both sides by 9. So you get 144 equals x plus 3. And then subtract 3. So you get x equals 141. Okay, this question here is kind of similar to the first question. We can't get the same base, so let's take the same, or just take a logarithm of both sides, make it the common logarithm, x plus 2, because then we'll be able to use our calculator again. 2x minus 3. We can use the power law now. We can bring this x plus 2 down, and be careful, that's 2 terms there, times log 3 equals, same thing here, power law, 2x minus 3 log 5. Next step, believe it or not, you're going to do mountains. Multiply those by log 3, multiply those by log 5. So you end up with x log 3 plus 2 log 3 equals 2x log 5 minus 3 log 5. Okay, now we're trying to isolate x. We want to get all our x's to one side. Actually doesn't really matter which side you move it to. So I think I'm going to move this x over to the right. It doesn't really make a difference. So what I have is 2 log 3. I'm going to move this negative 3 log 5 over, so I get plus 3 log 5 equals 2x log 5, and I'm moving this x log 3 over, so it's now minus x log 3. Alright, keep this the same. 2 log 3 plus 3 log 5 equals, you got to factor out an x. There's an x here and there's an x here, both of them in front of the logarithm. You can't do that if there's an x as the argument, but if they're both out front, you can do that. So we'll take out the x, and what we're left with is 2 log 5 minus x, or sorry, minus log, we took the x out, didn't we? 3. Hey, this is great. This means x times all that equals that. We can now isolate the x. How? Since this is x times all that, we're going to divide by all that. So we get x equals all this, 2 log 3 plus 3 log 5, divided by this whole amount, 2 log 5 minus log 3. But if it asks you to get a decimal answer, you could pick up your calculator right now and get the answer by plugging 2 times log 3 plus 3 times log 5, blah, blah, blah. But just so you're clear, you could simplify this a little more. You could use the power law to bring that 2 up. So you'd get log 3 squared plus log 5 cubed over log 5 squared minus log 3. And then from there we could make it log 9 plus log 5 cubed is 125 over log 25 minus log 3. That's a good answer. You could also now take your calculator and say log 9 plus log 125, or you could keep going. You could do log of 9 times 125, right, over log 25 over 3. It's getting a little crazy now, but you could still do that. So you'd end up with the logarithm of 9 times 125 is 1,125 divided by logarithm 25 divided by 3 is 8.3 repeating. I'm just going to keep it as 25 over 3. Okay, that's another way you could do it. You could pick up your calculator and type log 1125 over log 25 over 3, or, and now I'm just kind of showing off, what you could do is use the change of base formula, and you could say log the base of 25 over 3 of 1,125. This is also equal. So, I don't know, you could stop here and use your calculator. You could stop here and use your calculator. You could stop here and use your calculator. You could stop here, but most people won't be able to use your calculator here. I can on my calculator. But a lot of people, the calculator won't work here because it's not a common logarithm. So maybe one of these first three circles is the best. Anyway, again, I'm not going to use my calculator and do this, but when you do use your calculator and plug in whatever one you're going to use, you'll get some number like 3.3135. Goes on and on after that. Okay? Alright, don't get overwhelmed by that one. I'm hoping you can at least follow me down to this stage and probably this second stage here, the second bubble there. Alright, next, here's an interesting one. This is not a 2 that can scuttle off to the front, right? This 2 can scuttle to the front, the power law, but you can't use the power law here because the whole thing is squared. So let's keep that the same. The base 3 log of x all squared equals, let's scuttle the 2 over, 2 times the base 3 log of x plus 3. Now, if you look at that just a little bit, do you see that this is actually a trinomial that you can factor? Pretend log 3x is actually m. You'd have m squared equals 2m plus 3. And you could factor that, couldn't you? You could move all these over and factor. That's exactly what you're going to do here. These ones are kind of hard to spot sometimes, but this is like a trinomial. You have the base 3 log of x squared. Now we're going to bring this over, so we have minus 2 times the base 3 logarithm of x, bring the 3 over, minus 3 equals 0. We can factor that. We're looking for two things that multiply to 3 and subtract to 2. Oh, that's negative 3 and plus 1. And what goes at the front? Not just x, base 3 logarithm of x, and base 3 logarithm of x, because base 3 logarithm of x times base 3 logarithm of x equals base 3 logarithm of x squared, exactly what we had there. Okay, one of these brackets or both of them has to equal 0. So either the base 3 logarithm of x minus 3 equals 0, or the base 3 logarithm of x plus 1 equals 0. Let's solve both of them. The base 3 logarithm of x equals positive 3, and now we can change this into exponential form. We'd have the base to that exponent, 3 cubed, equals x, so x equals 27 is one answer. And this one we have, we got to move the 1 over first. The base 3 logarithm of x equals negative 1. Again, that means we can change it to exponential form. 3 to the negative 1 equals x, and that's a flippin' negative, it's 1/3. Both of those are positive and they don't equal 1, so it looks like we have a good answer here. You could check it out if you want by plugging it back in. Okay, they just keep getting harder and harder. Here we have different bases, so that's going to make it very difficult here when you have different bases. So you might want to try to use the change of base formula. Change of base formula will change this to log x over log 4, and it will change this one to log x over log 2, and this still equals 6. Now we still have different bases down below, but if you think of this, log 4, that's useful because we can change log 4 to log 4 is the same as 2 squared plus log x over log 2 equals 6. A lot of rewriting here. Okay, power law here. We have this argument squared, so we can scuttle the 2 out. We have 2 log 2 plus log x over log 2 equals 6. All right, now we're adding. You need to have common denominators. What do you need to multiply this denominator by to get 2 log 2? You have to multiply by 2. And what you do to the bottom, you have to do to the top. So we end up with log x plus 2 log x all over the denominator 2 log 2 equals 6. And I just don't have room to finish this, but I'll keep going here. Now, log x plus 2 log x, well that's like 1 log x plus 2 log x, so I have 3 log x over 2 log 2 equals 6. This is the same as 3 over 2 times all this. Like, look at this part separately. And what you can do here is you could use the change of base law and go backwards. So you'd still have 3 over 2, but it would be now log 2 of x equals 6. We're getting very close now. Why don't we now divide by 3 halves to get the 3 halves over here? So we have log 2 of x equals 6 divided by 3 halves. So log 2 of x, you got to flip and multiply, you'll get 12 over 3, which is the same as 4. And finally, you can use your changing it to exponential form. 2 to the 4th power equals x, that's a 4, and so it equals 16 is your final answer. My gosh, is that ever a lot of work? And that's very tough. I mean, that's going to be about as tough as you'll do this year. If x equals log c and y equals log a, then simplify this equation, or this expression right here, so that you only have x's and y's in it, no a's, no b's, all that kind of stuff. You have these as common logarithms, and these aren't common logarithms. You have log b. So base b. So often when that happens, you're going to use change of base formula again. So I'll do this one in black. So let's change all these with change of base formula. We have log c over log b. That's what this equals right here, right? And then we're going to minus log a over log b, which is what this equals. And all of that should be divided by, the next one would be log c over log b, and then plus log a over log b. Okay, now you have common denominators. If you just look at this portion here, you have common denominators. So you have log c minus log a all over log b, divided by, again, if you look now this portion here, you have common denominators. So you have log c plus log a divided by over log b. Now, this line right here means divide. So what we can do is take the top part, log c minus log a over log b, and divide it by the bottom, but when we divide, we multiply by the reciprocal. Log c plus log a. Why is that useful? Because you can now cancel these out. You're left with log c, which is x, minus log a, which is y, over log c, which is x, plus log a, which is y. So you're left with x minus y over x plus y. Okay, that's it. Tough stuff. Do your best. That's all you can ever hope for, all we can ever ask.